Hello and welcome. Today we're going to be taking a look at two different sections, 1.4 and 2.1, talking about properties of real numbers and linear equations in one variable. So we'll be looking at using the distributive property, using inverse properties, identity properties, commutative and associative properties, and the multiplication property of 0. And then in 2.1 we'll be looking at, again, those linear equations, so deciding whether a number is a solution for a linear equation. Also looking at determining or solving linear equations by using addition multiplication properties. Solve linear equations using distributive property, work with the linear equations with fractions or decimals, and then looking at identifying conditional, contradictions, and identities. So a few different things there. Getting started with our distributive property. Here's a little area model that can show that. So if you break it down into a 2 by 3 here and a 5 by 2 here, you get area of 6 and area of 10, or you can look at it as a 2 by 3 plus 5, which of course ended up being 2 by 8. So either way you get a total of 16 for the area, and that's really how the distributive property works. It's an area model type of explanation of that. And you can see at the bottom how we just like to draw those little loops showing how the single term distributes into that sum, and it works whether that A is on the left or the right. So here's a few examples of using the distributive property to rewrite an expression. So in the first one, we just take that 3 and we multiply it by the x and we multiply it by the y. So we get 3x plus 3y. That's all there is to that. With the second one, you might want to take a look at multiplying the negative 2 by the 5 and the negative 2 by the k. Again, just a little bit more complicated with the negative in there. We get negative 10 minus 2k as our result. Now for C, using the distributive property to rewrite that, we're actually going to use that in reverse. So we actually factor that x out and we get 4 plus 8. So we've already done what they wanted. You could go further and say, well, that's x times 12 or 12x. But again, we used the distributive property to rewrite that here, so that's really what we're trying to show, is how to use that distributive property in that way. For D, that's the same idea. We can factor an r out. We get 3 minus 7. And again, we did what they wanted. We rewrote the expression. For E, we cannot actually do that. There's nothing to be done there because there are no common factors that we can work with. And then F is a good example where we have more than two things to distribute to. So we get 6x plus 12y minus 18z when we multiply those through. We've got our inverse properties. So we have the a plus the opposite of a is 0. So again, those two really adding ones on top. And then we've got our reciprocal or inverse of multiplication property, a times 1 over a is 1, or 1 over a times a is 1. And then here we're just showing that the additive identity is 0, meaning that if we add 0 to something, we don't change the value of it. And the multiplicative identity is 1, meaning that if we multiply something by 1, we don't change its value. So here, it's just a different way of thinking of that identity property that 1 times a is a. Sometimes people struggle with 12m plus an m, but if you think of the m as 1m, that can help. Then you can see that you're really going to add the 12 and the 1 together and get 13m as the result. Likewise with the y plus y, it's really 1y plus 1y for a grand total of 2y. And we can think of the negative as a negative 1, and then we can distribute that through, so we get a negative m plus 5n. So again, just kind of helps sometimes to be able to see that in a little bit different way. Okay, so the commutative and associative properties, again, we've got commutative for both addition and multiplication, and associative for both addition and multiplication, so we can rearrange things the way that we want to, really. So for this first example, what I might do is just use my commutative property to rewrite this so that my like terms are together. Oops, I forgot my M there. So I can do that, and then generally we kind of just go through and do our stuff, but really what we're saying here is we'll do the adding first, so I'm using an association there in order to add those together. We don't always think of it that way, but that's really what we're doing. And then the 3 and the 8, we could add that to be 11. And then again we could group this, the 3m minus the 6m gives us negative 3m plus 11. And of course we can't do any more because the negative 3m and the 11 are not. So simplifying these expressions, kind of a long way to look at this first one is that we could think of it as factoring that y out. So we have our 5 minus 8 minus 6 plus 11, and factor that y out. So then it's just a matter of combining those. So I might think of combining the negatives to get negative 14 and the positives to get a positive 16 without actually redrawing that, but I'm really using the commutative and associative properties there. And then we end up with a grand total of 2y. B is a good example of a problem that tends to give people trouble. Whenever we have this here that they've highlighted, then people tend to have an issue with distributing that negative through. My recommendation, change that minus to adding and then a negative 5. That should help distribute that through. There's a little simplification we could do besides that, but we could, well actually let's go ahead and do that. So I got the plus 4 and a minus 8, so that's going to be 3x minus the 4. And then distributing the negative 5 through, I get minus 5x and then minus 5. I can combine the x's, 3x and a minus 5x for a grand total of minus 2x. And minus 4 and minus 5 would end up being minus 9. For the next example, the 3x times the 5 times the y, again it's just multiplication, the parentheses there just to emphasize the different factors in that product. We can really only multiply the 3 and the 5 together, so I'll use the commutative property of multiplication to rearrange that, and we can just drop those parentheses. 3 times 5 ends up being 15. Again, notice there's no adding or subtracting in there, so we don't have an example of a distributive property. That's a common mistake people make. And then the next one, we've got that subtraction there. So the 8 and then the minus. Again, it can be helpful to think of that as minus 1 and then distributing that through, or if we want to change it to plus a negative 1 and distribute that through. Then we can see we get 8 minus 3m minus 2. We can do the 8 minus the 2 to get 6, and then minus the 3m. So it looks like that. So a linear equation in one variable can be written in the form a times x plus b times y equals c, or sorry, a times x plus b equals c. Where a, b, and c are real numbers, and then a isn't equal to 0, because if a were 0, then it wouldn't really be linear anymore. So we're going to go ahead and solve this equation. We do have a set of steps that we can use in order to do that, so if you want to pause and read through that, that's fine. I'm just going to kind of go about using those without necessarily talking about each one every time. I would probably start by combining like terms on my left side there. The 4x minus 2x would give me 2x. Still have the minus 5. And on the right side, the 4 and the 3 makes 7, so I'd have 6x plus 7. Now, I've got both sides simplified, so I would probably start doing operations to both sides. Personally, I prefer to work with the variables first here, so I would subtract 2x. So I get negative 5 equals 4x plus 7. And then I've got my x's on the right, so I'd want to move everything else over to the left. Get negative 12 equals 4x. That will divide nicely for me. Dividing by the 4 to get the x by itself, we get x equals negative 3 as the result. And you can always check your answer by plugging it back into the original for all of your x's and make sure that it actually works out. Okay, so a few other equations that we will solve. The first one involves using the distributive property. So we would distribute the 2 through, we get 2k minus 10 plus the 3k equals k plus 6. On the left side I've got 2k and 3k that are together on the same side there. Trying to make that look better. So the 2k and the 3k both positive, so we have 5k. Oops, not x. 5k minus 10 equals k plus 6. Again, like I said on the last one, I do prefer dealing with those variables first, so I will subtract the k. It gives me 4k minus 10 equals 6. I can add the 10 to both sides. It gives me 4k equals 16, so again that will divide nicely for us. We get k equals 4. And again, we can check by plugging that back into the original. Looking at the example 3, solving an equation that has fractions in it. Notice that the denominators are 6 and 2. The least common multiple of 6 and 2 is 6. So if I multiply both sides of the equation by 6, that will eliminate all of the fractions, which is very nice to have done. The 6 will distribute here, so we're using our distributive property. When it multiplies the x plus 7 over 6, the 6 will just cancel. When it multiplies the 2x minus 8 by 6, the 6 will get cut in half, so it's really just 3 times the 2x minus 8. And then the negative 4 times 6 will be negative 24. It's very common, and honestly I just about did it myself just there, to forget to multiply the other side of the equation by the 6 because we spend so much time with those fractions. At this point I just need to clean up my left side a bit. So distribute this 3 across. So we get x plus 7 plus 6x minus 24 equals negative 24. It's a little tempting to just add that 24 to both sides, but I'll go ahead and kind of solve this more normally. So x and 6x makes 7x. 7 and 24 makes minus 17. Add the 17 to both sides. We get 7x equals negative 7. Dividing by 7, we get x equals negative 1. And so that's what that one looks like. Again, you can always check by plugging that back into the original and making sure that that works. And the last one on this slide. For example 4, since the decimals are all in the hundredths, then if we multiply both sides of the equation by 100, that will eliminate all of those decimals for us. So sneaking a 100 on each side of that equation. Distributing on the left, we get 6x plus 9 times 15 minus x. And on the right, we just get 7 times 15. So now we just need to simplify. So again, getting rid of those decimals makes that quite a bit easier. We'll have to distribute on the left side. So we get 6x plus 9 times 15. We'd be looking at 135 minus 9x equals 7 times 15 would be 105. From here we would combine like terms on the left side. We've got the 6x minus the 9x, so it's a negative 3x plus the 135 equals 105. So my variable is on the left, so even though it's negative, we'll just go with that. Subtract the 135 from both sides, we get negative 3x equals negative 30. Divide by the negative 3, we get x equals a positive 10. So x equals 10 for that one, and again, we can always check by plugging that back into the original. And bringing us to our last slide, looking at determining whether a equation is a conditional equation. It could be an identity or it could be a contradiction. So we still solve the equations like normal. A conditional equation is like what we've been doing, where there is one solution. So if we look at our first example, I don't really have anything to do on the left side, but we would distribute the 4 on the right. Subtracting the 4x gives us x minus 9 equals negative 12. Add the 9 gives us x equals negative 3. So this is what we call a conditional equation. It's true so long as x is negative 3. The second equation, nothing to do on the left side. We distribute the 5 on the right side. At this point, you may notice that the left and right side are exactly the same. If you want to stop and say that that's an identity, that's perfectly fine. If you need to continue, you can go another step and subtract 5x from both sides. Get negative 15 equals negative 15. This is typically where we go to in order to solve these equations. What happens is all the variables are gone, and we're left with a true statement. That is an identity then. That means that the solutions for that equation are all real numbers. So any real number you plug in there for x, and you will get a true statement that will make that equation true. Looking at the third and final one, you might be able to guess what happens here. We do need to distribute the 5 on the on the right side. So we get 5x minus 20. Now notice they're not exactly the same, but they both have a 5x. So if we subtract 5x from both sides, we get negative 15 equals negative 20. Well, that's not true. So this is never true, which means that it is a contradiction. It's never true. So there is no solution for that. Generally, I am going to be looking for a couple things. I guess I didn't do it over here. The solution and what type of equation it is. So like for the first one we did, solution is x is negative 3 and it's conditional. For the second one, that's an identity. So the solution is all real numbers. And there's shorthand for that too if you know how it looks. And then the third one was a contradiction, and so that means that there is no solution. And that's how we deal with identities and contradictions, and of course very used to dealing with conditional equations without even thinking about the fact that they are conditional. Thank you very much for watching, and hopefully that helped.